Well, good morning. Once again, we appear to have missed a day of class due to inclement weather, so I'm going to try to talk us through some examples from section 11.3 and then later from section 11.4. So we did discuss the information here in 11.3 about unit tangent vectors. Remember, a unit tangent vector is the derivative of r divided by the magnitude of r, if r is our differentiable vector valued function. And so we said the unit tangent vector will always point in the direction of motion along the path that maybe the projectile or particle is traveling. And then after the unit tangent vector, we developed the unit normal vector. Unit normal vector is normal or orthogonal to the unit tangent vector at any given point that you choose it, and that you can find the unit normal vector by taking the derivative of t and dividing by the magnitude of that derivative of t. So once again, that will produce a unit vector. And lastly, in class on Monday, we talked about the binormal vector, b of t, and it is found by crossing t with n, and then that binormal vector can be used to find the equation of the oscillating plane at r of any t sub 0 value. So there's the, graphical depiction of what's going on. This would be in a 3D realm. We have t being parallel to the direction of motion at this particular value, n pointing into the curve and perpendicular to t, and then b, the binormal vector, being perpendicular to both n and t, and being a normal vector that you can use for finding the equation of the plane that contains n and t. And then that plane would be a good representative of the function in that area. Alright, so what I want to do is actually work a problem with this. Let's move over here. Okay, so given that r is e to the t, e to the negative t, t square root of 2, find t of 0, n of 0, b of 0, and the equation of the oscillating plane at time t equals 0 as well. So we've got to find the unit tangent vector, the unit normal vector, the binormal vector, and the equation of the oscillating plane. So we go through these processes one after the other in that order. We need to find t sub 0 first, then n of 0, then b of 0. So t of 0 requires us to find r prime of t and the magnitude of r prime of t. So simple derivative, remember the derivative of r is equal to the new vector function whose components are simply the derivative of the vector components of r. So derivative v of t is e of t, derivative of e to the negative t is negative e to the negative t, and the derivative of t square root 2 is just square root 2. The magnitude is found by squaring each component, summing their values together, and then taking the square root. So we have r prime, we have the magnitude of r prime, therefore we can produce t of t, r prime of t divided by the magnitude of r prime of t. And so that's the function that would give you the unit tangent vector at any time t. We care particularly about t of 0, so finding that vector simply requires us to plug in 0 in to that equation, and we get the vector you see there at the end. 1/2, negative 1/2, square root of 2 over 2. Notice the magnitude at 0 ends up becoming the square root of 4, which is just 2. And then plugging in 0 into r prime is also a trivial task. I'm going to once again move this up here because I think we'll have more work show up down here and don't want to block it by the video of my face. Alright, so that's the first piece. We have 3 more pieces to find. We need n of 0. Before you can find n of 0, you need n of t. Because we don't want to just take the derivative of t of 0, because the derivative of a constant vector is going to be the 0 vector, since all the components are 0. So you have to go back to t of t, and we need to take the derivative of this to produce n of t. So n of t is going to be t prime of t divided by the magnitude of t prime of t. So how do we find the derivative of that? Well, we look at it as by component. So we first need to find the derivative of e to the t divided by the square root of all that stuff. Then we'll find the second component by taking the derivative of negative e to the negative t over the square root of all that stuff. And the last derivative for the z component would be this derivative of the square root of 2 over the square root of all that stuff in the denominator. So basically you have three applications of the quotient rule. So I never promised that this would be easy. It's a lot of work often to come to the final answer in these problems. So I'm not going to put all the steps here, but if you do those quotient rules correctly 3 times, you'll notice that the quotient in all cases has the same denominator, and then there are the numerators, so that is t prime of t right there. So rather complicated. And if you think about it, we're only halfway to n of t, because n of t is t prime of t divided by the magnitude of t prime of t. Now that is not exactly the most fun problem over which to find the magnitude. Notice we'd have to square each component, add them all together, and take the square root. So it's pretty horrendous. So what we can do at this point is do a shortcut. Let's just, now that we know what t prime of t is, let's find t prime of 0. And since we only care about the unit normal vector at 0, we can then find the magnitude of that specific vector as opposed to the magnitude of the t prime of t. So to find n of 0, we can plug 0 in here for t. If you do that, we will get that t prime of 0 is 1 over 4 to the 3/2, that's what the denominator becomes, times the vector 4, 4, 0, which if you distribute and simplify that, that's 1/2, 1/2, 0. So a very nice, easy to work with vector at that point, 1/2, 1/2, 0. And so n of 0 requires us to divide t prime of 0 by the magnitude of t prime of 0. So we can take the magnitude of that vector by squaring each component and taking the square root. So 1/2 squared plus 1/2 squared gives us 1/2. The square root of 1/2 is 1 over square root of 2, or 2 to the negative 1/2. And so last step, n of 0 would be to take t prime of 0 divided by the magnitude we just found, and if you simplify that, it's square root 2 over 2, square root 2 over 2, 0. Again, I'm leaving a lot of the algebra to you here. You should be able to verify that that is the answer here. Remember, calculus itself is not difficult. It's the algebra that trips a lot of people up, so make sure that you can do that algebra. So we have two pieces now, t of 0, n of 0. We need to find b of 0 next. b of 0 is simply produced by taking the cross product of t of 0 and n of 0. So this was t of 0, this is n of 0. If you do their cross products correctly, you come out with this vector for b of 0. Negative 1/2, 1/2, square root 2 over 2. Again, I'm leaving the details to you. Make sure that you can find that cross product and verify that that is in fact the value of b of 0. Last thing to do is to find the equation of the oscillating plane. Now the oscillating plane, or any plane for that matter, just requires you to have a point on the plane and a normal vector. Well, b of 0 is a normal vector to the plane, but we can use any normal vector. So why not use one a little simpler? For instance, if we multiply b of 0 by 2, we'd produce the vector negative 1, positive 1, square root 2. And then we wouldn't have to deal with fractions. So here it is, negative 1, positive 1, square root 2. And then I'm going to dot that with x minus 1, y minus 1, 0, and that has to be the 0 vector. That has to be the value of 0. This is a scalar, not a vector. Now, where do we get this right here? I used the terminal point of r of 0, so we plugged in 0 up here, and we get 1, 1, 0. So that will be a point on that plane, 1, 1, 0. And so if you subtract 1 from x, subtract 1 from y, and subtract 0 from z, and then dot it with our normal vector, it has to equal 0. So finishing it out, distributing the -1, the +1, the square root 2, and combining constants produces -x plus y plus z times the square root of 2 equals 0 for the equation of our oscillating plane. So that's a problem putting together everything from section 11.3 regarding unit tangent vectors, unit normal vectors, binormal vectors, and the equation of the oscillating plane. You need to be able to find all 4 of those items for a given vector valued function R. So you obviously have several of these to practice in WebAssign, and also on the worksheet from 11.3 you should have 1 or 2 of these to complete as well for Wednesday's class. In a few minutes I'm going to put together a video on 11.4 just so I can introduce the material there. We'll pick up with 11.4 probably on Wednesday as well. So thank you very much.